Welcome. In this multivariate calculus tutorial, we are going to mainly focus on parametrization, and so sketching curves in a parametrized form, going back and forth between a parametrized form and an XY equation. And then we'll use parametrization in various applications, including line integral, and work done. Okay, so let's begin with question 1. And so question 1 says, sketch indicating an arrow as t increases the curve x equals 1 minus t squared, y equals 2t minus t squared, where t is between minus 1 and 2. So the first thing you want to do here is work out a place where you start, and that's when t is minus 1. Work out the place where this should finish, t is 2. Then eliminate t in the equation, find what curve, and then proceed to sketch that curve. All right, so we have x of t, y of t, and this will be a point on our curve depending on t, given by the point 1 minus t squared, 2t minus t squared. And so let's call a the point where we start. We start at a, which is equal to x of minus 1, taking that minus 1 from the lowest t value, y of minus 1, and then we just sub in minus 1 wherever we see t. So that's 1 minus minus 1 squared, 2 times minus 1 minus minus 1 squared. Okay, so let's simplify this. This is 1 minus 1, and then over here we have minus 2 minus 1. So this gives us the point 0 minus 3, and this is where we're starting when t is equal to minus 1. Okay, so we finish at, say, the point B, which is x of 2, taking the 2 from our upper bound for t, y of 2, and then we take the number 2, sub it in everywhere where we see a t to find the point where we finish. So 1 minus 2 squared, 2 times 2 minus 2 squared. And so simplifying this, we have 1 minus 4 is minus 3, 4 minus 4 is 0. So B is the point minus 3, 0. Okay, so next, let's look at these two equations where we're given x in terms of t, y in terms of t. Let's eliminate t and then get a relationship between x and y without the t in it. Okay, so first thing we might want to do is, well, let's subtract equations here. So equation 1 minus equation 2 give us x minus y equals, now the minus t squareds in here will vanish. So we have 1 minus 2t. Okay, and so next I can solve this equation for t. So taking the 2t over to the left-hand side and the x minus y over to the right-hand side, we have 2t equals 1 minus x minus y, so that's plus y minus x. And then if we divide this by 2, we get t is equal to 1/2 brackets 1 plus y minus x. Okay, so now we can take this and substitute that into the equation for x up here. So x is equal to 1 minus the square of this. So that's 1/4, 1 plus y minus x squared. Okay, we can probably do a little bit more with this. So we can say multiply by 4. Okay, so we have a nice relationship between x and y here. And so we can see that this is a quadratic relationship, but it's not exactly with its axis of symmetry on the x or y axis. So it's a little bit more complicated than that. So now what we might want to do is just find a few other points on the curve. So we'll say when t is equal to 0, we have the point xy, 1 minus 0 squared, that's 1. 2 times 0 minus 0 is 0. So we have the point 1, 0. Okay, when t is equal to 1, we have the point 1 minus 1 squared is 0. And then 2 times 1 minus 1 squared is 2 minus 1 is 1. Okay, and so now we should begin to sketch this because we know that this is a quadratic relationship. So I'll just draw some axes. Okay, so where do we start? We start with the point 0 minus 3. So that's here. Let's label that A. And then we finish at the point minus 3, 0. So that would be here. Okay. And then we have point 1, 0 when t is 0. That's here. We have point 0, 1. It's here. And then we know that this starts here, finishes here, passes through these points, and it has a quadratic shape. And so it must look something like this. Okay, and so the arrows on this that we'll put now indicate the direction that it goes as t increases. All right, so we're done with that. Now I will show you a Mathematica plot, except what I've done here is animated this. So I'll just move this along. What I've animated is the red point. So this is the position on here as t increases. So it's like a particle following a trajectory. Question 2, we have x equals t cubed plus t, y is equal to t squared plus 2, and t is between -2 and 2 inclusive. So the question asks us to sketch indicating an arrow as t increases. So we again want to find, where does this start, where does it finish? So let's call A the starting point. So this is x of -2, y of -2, which is -2 cubed -2, and that is -8 minus 2 is -10. Y of -2 is -2 squared plus 2, so we have 4 plus 2 is 6. So the point -10, 6. Okay, so finishing at the point x of 2, and this should say 2 up here. So x of 2, y of 2. So we have 2 cubed plus 2 is 10. 2 squared plus 2 is 4 plus 2 is 6. So we finish at the point 10, 6. Okay, so now let's find a few more points. So when t is -1, we have -1 minus another 1. We've got the point -2, and then 1 plus 2 is 3. Okay, when t is equal to 0, we have 0 for x, and then we have 2 for y, so 0, 2. When t is equal to 1, we have 1 cubed is 1 plus 1, so that's 2, and then 1 squared plus 2 is 1 plus 2 is 3. Okay, and so this should help us sketch this, but we also might like to have a relationship between x and y. So let's eliminate t in the expression to find a relationship between x and y. Taking that second equation, we have t squared is y minus 2. So t is plus or minus the square root of y minus 2. Okay, and so now we can take this and substitute that into the first equation. So x is equal to the square of this times t, that's t cubed. So we have y minus 2 in brackets times plus or minus the square root of y minus 2, and then plus or minus the square root of y minus 2. Okay, so we'd probably rather not have a plus or minus in here. So let's factor out the plus or minus square root of y minus 2. So then we have left over y minus 2 plus another 1, which is y minus 1, and this is x. So now if we square both sides, we can get rid of this plus or minus and the square root. So we have x squared equals y minus 2 times y minus 1 cubed. Or sorry, squared. Y minus 1 squared. Okay, so now we have a nice curve representing the relationship between x and y. Okay, so this appears to be an elliptic curve, and so we kind of know what that looks like, but this is not in the usual form, right? Normally an elliptic curve would be expressed as y squared equals some cubic. So this will be an elliptic curve rotated 90 degrees. Okay, so this should be enough to sketch this now. So when t is minus 2, we have minus 10, 6. So let's put that there. And then on the other side, we have 10, 6. Then when t is minus 1, we have minus 2, 3. So something like this. And then when t is 1, we have 2, 3. So there seems to be a little symmetry about the y-axis. When t is 0, we have 0, 2. And that seems to be so far the lowest y value. Okay. And so this being an elliptic curve, it's going to look like something like this, with the arrows going left to right, because we start at minus 10, 6 and we finish at 10, 6. All right, so now let's plot this using Mathematica. So I'll change the previous plot. Now what I need to change here is this coordinate. So t cubed plus t, and then this should be t squared plus 2. We change the starting point, minus 2 to 2, and the finish point. And then I'll just copy this, put it here. And then I need to make my plot range able to accommodate the start and the finish. So our start is, we need at least 0 to 6 in range. So let's try this. Okay, and so do we have a point moving along? Yes, we do. And there we go. just like what we have here. Okay, question 3. Here we have x equals 2t minus 1. Y is a half t plus 1. So we only have a power of 1 in each of these. So this is a linear relationship between x and t. So let's read the question. Sketch indicating an arrow as t increases. Find the Cartesian equation of the curve. Okay, so that means we need to eliminate t. Now notice we don't have a starting point or a finishing point. So this is over all real numbers t. Okay, so what we want to do here is multiply the second equation by 2. So we have 2y equals t plus 2. Take the t over to the left-hand side, and so that we have t equals 2y minus 2. Notice I've swapped sides as well. Now we can take this and sub that into the first equation. So we get x equals 2 in brackets 2y minus 2 and then minus 1. So expanding this, we have 4y minus 4 minus 1 is 4y minus 5. Okay, now if you want to put this in the standard form so it's clear to see what the slope is, then we need to take that 5 over and divide by 4. So we're going to get y equals 1/4 x plus 5 over 4. Okay, so we can sketch this curve quite easily. So the slope here is 1/4, so something like this. So we rise 1 and we go over 4, and it's a positive slope. So parallel to this, okay, but the intercept is 5 over 4, which is 1 1/4. So here, so I want to make it parallel to this line. So something like this. Okay, and now the arrows as t increases, well, you need to think about what is happening as t increases. Well, you can see x increases also, and in fact, you can differentiate this with respect to t. So x dash of t is 2. That's positive. So that means as t increases, x increases. So arrows go left to right. Okay, so just like that. So let's put our arrows on this. And there we go. We're done with question 3. So let's move on to question 4. Sketch indicating the arrow as t increases. Find the Cartesian equation of the curve. Okay, so we have x equals t squared minus 3. Y is t plus 2. T is between minus 3 and 3. Okay, so where does this start? Let's call that A. We sub in minus 3 for t. So we have minus 3 squared minus another 3. So that's 9 minus 3, which is 6. And then minus 3 plus 2 is minus 1. The finishing point, let's call that B. Now we're subbing in 3. So we have 9 minus 3 is 6. And 3 plus 2 is 5. So we finish at 6, 5. Okay, let's find a few other points. So when t is minus 2, we have xy is minus 2 squared minus 3. So that's 4 minus 3 is 1. Minus 2 plus 2 is 0. Okay, when t is minus 1, we have minus 1 squared is 1. 1 minus 3 is minus 2. Minus 1 plus 2 is 1. When t is 0, you don't have to stick to the integers, by the way. I just think it makes it easier to find a few points and fill them in. Okay, so when t is 0, we have minus 3, 2. When t is equal to 1, we have 1 minus 3 is minus 2, and then 1 plus 2 is 3. When t is equal to 2, we have 2 squared is 4. 4 minus 3 is 1. 2 plus 2 is 4. Okay, so we have a bunch of points here. Now, let's find the relationship between x and y. So t is y minus 2, and so we can sub that in there where we have t in the first equation. So that's x equals y minus 2 squared, and then subtract 3. Okay, and so this is a parabola. And you might like to think of this as a parabola on its side. Y equals 2 should be our axis of symmetry. Okay, so let's sketch this now. Okay, so there's y equals 2. Now, we start at 6 minus 1. That's A. And then we finish at, oh no, that's, yeah, that's right, 6 minus 1. Okay, so then we finish at 6, 5. So 1, 2, 3, 4, 5. That'll be up here. Okay, then we have a point 1, 0. We have a point minus 2, 1. we have a point minus 3, 2, then we have a point minus 2, 3, and then we have a point 1, 4. So there, and we know that this is a parabola. Minus 2, 1 should be here, right? Okay, there we go. Not here. So we know that this is a parabola, so it appears to be minimum here along the axis of symmetry. So just fill in a parabola there. And where do we start? We start at A, and we finish at B. So something like that. Okay, question 5. X equals sine of t, y is 1 minus cos of t, and t is between 0 and 2 pi. Okay, so we want to exploit the relationship between sine and cos that says cos squared plus sine squared equals 1 to find the relationship between x and y. Okay, so we have x squared is sine squared of t, and then if we take this cos over to the left-hand side and the y over to the right-hand side, we can write cos of t is 1 minus y, but if we square that, we have cos squared of t is the square of 1 minus y. And so now let's add cos squared and sine squared. So here we have then 1 minus y squared plus x squared is equal to 1. And so we can recognize this as a circle of radius 1. Let's write that in the standard form. So x minus 0 squared plus. Now, since we're squaring this, I can write this as y minus 1 squared because minus 1 squared is 1. So there's the circle in the standard form. So this has radius 1 and center the point 0, 1. Okay, so that should make this easy to sketch. So let's find our center. Let's put it here, 0, 1. Okay, and it has radius 1. So something like this. Okay, now where do we start? We start when t is 0, and so that's at the point x equals 0, y equals 0. So we start here at the origin, but cos and sine are periodic functions of period 2 pi. So we also finish at the same place. So now the question is, how do we determine which way this is? Is it counterclockwise or is it clockwise? And so to determine that, if we just fix the point 0, 0 and look at the derivative, what's going on with x dash, what's going on with y dash. So x dash as a function of t is cos of t. So x dash of 0 is cos of 0, which is 1. And that's positive. So that says it's going left to right at 0, 0. Now, the y should be increasing as well at that point. So y dash of t is the derivative of 1 minus cos of t. So the derivative of cos of t is minus sine of t. So we have minus minus sine of t, which is sine of t. And so y dash of 0 is sine of 0, which is 0. Now I said that was supposed to be positive, but it's positive. You're slightly on this side of it. It's exactly 0 at this point. Okay, and so from this we determine that it's going counterclockwise, mainly from this one. Okay, question 6. Sketch indicating the arrow as t increases. Find the Cartesian equation of the curve. Here we have x equals e to the t, y equals e to the minus 2t. Now notice here, there's an e to the t in this because we can write this as e to the power of t all to the power of minus 2. And so we see then, since e to the t is x, that y is equal to x to the minus 2, which is 1 on x squared. Okay, so let's sketch this here. This is, well, it's not quite a hyperbola because we have a square there. And so on this side, it looks like a hyperbola with asymptote x-axis and y-axis towards the positive end, but on this side it does a similar thing here. So something like that. All right, I'll open up Mathematica and give you a sketch of this. Okay, and so there we have a computer-generated sketch of the same thing. Question 7, here we're sketching x equals e to the 2t, y equals t plus 1. Okay, so here we want to solve this for t. T equals y minus 1. So if we sub that in to this t here, we have x equals e to the power of 2y minus 2. And so we have exponential increase. Okay, also, because we're going to determine the direction of the arrows here, let's take x dash. So we have 2e to the 2t. And so this is positive for all real t. Y dash of t is 1, and that is positive for all real t also. So the arrows go left to right and from down to up. Okay, and so now let's find a few points on this. So when y is 1, we have e to the 0. So we have the point 1, 1. When y is 0, we have x is 1 on e squared. When y is 2, we have e squared for x. And when y is minus 1, we have e to the minus 4. So 1 on e to the power 4. Okay, and so let's sketch this. So normally we would draw e to the x something like this, right? But this is e to the 2y minus 2. So we've got to think in terms of this way when we sketch this. Okay, so let's find the point 1, 1. Then we have a point, say, here. We have a point. So what is e squared? Hang on. exp 1.0, and then let's square this. So 7.389. So somewhere out here, we have another point. Okay, so what this is doing is it's going to look something like this. Got a bit of a dodgy drawing here, so let me do this again. So I'll copy out that code, except I'm going to use contour plot just to make this easier. Contour plot, and then I'm going to write in our equation. So x equals exp 2y minus 2. I also need to include the y bounds here. Actually, I want this to go up to 8 and probably this to go up to, say, 3. Okay, so something like this, which is what I tried to draw here. Okay, question 8. Suppose that the position of one particle at time t is given by x1, y1. I'm going to write this somewhat differently. Is 3 sine of t, 2 cos of t, for t between 0 and 2 pi, and the position of a second particle is given by cos of t minus 3, comma 1 plus sine of t, for t again between 0 and 2 pi. Graph the paths of both particles. How many points of intersections are they? And that means in the intersection of those two equations, two curves. All right, so let's do this part first. So part A, what we want to do is find the Cartesian equation of the curve that represents the collection of points. And so again, we have cos squared plus sine squared equals 1. So let's write 1/3 of x1 is sine of t, and 1/2 of y1 is cos of t. So squaring both of these and adding the result, we've got 1/9 x1 squared plus 1/4 y1 squared equals sine squared plus cos squared, which is 1. And so this is the equation of an ellipse. So to write this as an ellipse in the standard form of an ellipse, we would have x1 over 3 squared plus y1 over 2 squared equals 1 squared. Okay, and so while we're at it here, let's sketch this ellipse. Now, the way I like to think about sketching an ellipse like this is to just pick a couple of points. For example, when y1 is 0, how would I get this to equal 1? Well, I would need to have x1 is plus or minus 3. So 1, 2, 3. I have a point here. Likewise, point over here on this side. Okay, and when x1 is 0, how do I have this to be equal to 1? Well, I would have to have y1 plus or minus 2 here or here. And then I just sketch an ellipse, just something like this. Okay, so there's my ellipse. All right, so now let's do the other equations. So for this one, we want to write, and again, exploiting cos squared plus sine squared equals 1. So we want to write cos of t is x2 plus 3. And then sine of t is y2 minus 1. Okay, so squaring both of these and adding the result, we have cos squared t plus sine squared t, which is 1. But that is x2 plus 3 squared plus y2 minus 1 squared equal to 1, because cos squared plus sine squared is 1. And then this represents a circle. So this is x2 minus 3, y2 minus 1. So we can see that the center is the point minus 3, 1. And the radius is 1. Okay, so now let's sketch this. Yeah, so our center is at minus 3, 1. So let's find that first. 1, 2, 1, 2, 3, and then up here. So our center is here, and then we have radius 1. So it comes down to this point, something like this. Okay, so we can see that we have two intersections. So let's write that. Two intersections. We can see clearly that one of the intersections is at -3, 0, and then the other one is found by solving. Let's write this other found by solving the system x squared on 9 plus y squared on 4 equals 1, together with x plus 3 squared plus y minus 1 squared is 1. And so the way I would go about this is eliminating y in the equations and then solving the result. But you can do this in Mathematica easily using the resultant, and I'll show you how to do that here. So let's just write resultant. So what I want to enter here is x squared on 9 plus y squared on 4, and then subtract 1. Taking this 1 here over to the left-hand side, so I have 0 on the right-hand side. And then I enter the other equation in the same way. So x plus 3 squared plus y minus 1 squared minus 1. And I want to eliminate y. Okay, and so now I want to factorize this. So I'll just write factor in front of this, putting a square bracket around it. So we can see a factor, and interestingly, -3 is a root. So let's write this down. So this polynomial equals 0, where we have x satisfying that simultaneous system of nonlinear equations. We're not asked to find this, but just to show you how you would do it if you had to. All right, and so to find any other solutions, now I would expect this polynomial right here to have one other real solution. So let's write nsolve this equals 0, shift and enter. So yes, we have one other real solution. And so the other point has x value minus 2.097 and so on. The y value is obtained just by taking this particular x value and subbing that back into one of these equations. So if I take that and sub it into this equation for the ellipse, well, I'll just take that whole thing, and then I'll use a replace all command /dot paste that. Okay, and so now I'm looking for all y such that this holds true, equal to 0, and let's just write solve. Okay, and so we have y equals plus or minus 1.43, but we know since the center is at -3, 1, that it's not the negative value, so it's the positive value, 1.430, let's call that. Okay, so part B now, are any of these points of intersection collision points? So for these to be collision points, these 2 points have to intersect at the same time, so same t value. So let's have a look at part B then. So let's first consider the point of intersection -3, 0, and find what the corresponding t value is, and do those match in both of these. Okay, so let's say, suppose this is equal to 3 sine t to cos of t. So what's the t value? So then we would have sine of t equal to -1 and cos of t equal to 0. Okay, so here I've just roughly plotted sine and cos. So this happens when t is 3 pi on 2 plus 2 pi k, where k is an integer. Okay, so next what we need to do is sub that particular t value in to the second point and see whether that gives us -3, 0, so this point of intersection here. So substitution into this equation here gives cos of 3 pi on 2 -3, 1 plus sine of 3 pi on 2, which is, now cos of 3 pi on 2 is 0, so we get -3. Sine of 3 pi on 2 is -1, so we have 1 minus 1 is 0. So yes, the point -3, 0 is a collision point. And next, let's do the same thing with this other point of intersection that we found, approximately this point right here. So we'll say for minus 2.097 1.430. Let's do the same thing. So we'll solve 3 sine t equals minus 2.097. 2 cos of t is 1.430. So I'll open up Mathematica here and do this numerically. Okay, so you can see what I've done here. So I put in nsolve, I put in that simultaneous system. It turns up nothing. And the main reason this could occur is because I've just taken truncated versions of this approximated point that we found here. But if instead I divide one equation by the other and seek out t such that the tan is this number, then I get a t value. Okay, so next let's take that and sub it in and see if we get approximately this number here. Okay, yes, that does hold true. Let's try the same thing with 2 cos, 1.43. Yeah, so this looks like a reasonable t value. Okay, so next we want to see if that satisfies the other point, as in this one. So take this little piece of code, copy it down here. Let's leave a bit of space, and then I'll put in cos of t minus 3. What do we get? We get minus 2.2849. So no, that does not give us the correct x value of this point of intersection here up at the top. So let's just double check by doing that with 1 plus sine of t. Okay, so no, we get 0.3 or so when we sub in this t value. So this point up here is not a collision point. It is an intersection of the two curves, but it's not a collision point. Only this point down here is a collision point. Okay, so next, let's take this and animate this in Mathematica by, first of all, I will do a contour plot of both of those curves. X squared on 9 plus y squared on 4 equals 1. And then we'll do the same thing with the circle. X plus 3 squared and then plus y minus 1 squared equals 1. X goes from, well, minus 4 to 3, and y goes from minus 2 to 2. Okay, so let's have a look at this. It's made this look like a circle when it's not, so we want to change the aspect ratio here. Okay, there we go. So there's a computer plot of this here. So now the animation part of it is, so let's call this A, and I'm going to suppress the output. Now what I want to do is write these points. Okay, so let's go list plot, and I'll make that pair of points. So I'll take this as t goes from 0 to lowercase a. I'll need to clear that first, and we'll call this B. And then I want to put some options in here. Oh, hang on. What am I doing? I'm jumping ahead of myself here. So I need to cut this, leave this as is for now. Okay, then we'll put show A and B together, but we wanted some options in here. So plot style. Let's make the points red and increase the point size. I like to choose 0.02. That makes it somewhat big, but not too big. Okay, then show AB. Now the part that's going to change here is this part because T will be changing. So let's write manipulate after the A, and then I'll press Control V. Okay, and now I'll run this and see what happens. Okay, so when T is 0, here are our two particles. I need this to go to 2 pi. Okay, so let's see. All right, so as I move this slider around, the two particles are moving. Right, so you can see this one on the left passes that point of intersection of the curves, but it's not an intersection in time, so it's not a collision point. Right, but as I keep going, you'll see they do collide at -3, 0, but they never collide here at this second point of intersection. All right, so I think I will leave the third part of this, part C, to you to do, and I'll move on to question 9. Next, y dash of t is the derivative with respect to t of 1 plus t to the power of a half. So using the chain rule here, we bring down the 1/2, subtract 1 from the exponent. We have 1/2, 1 plus t to the 1/2 minus 1 is -1/2, and then multiplying using the chain rule by the derivative with respect to t of that inside function, 1 plus t. But of course, this derivative is just 1. Okay, so we have 1/2, 1 plus t to the power of minus a half, which we can write as y dash of t is 1 over 2 root 1 plus t. Okay, so using this result, dy on dx is 1 over 2 root 1 plus t over x dash, so 1 over 1 plus t squared. Now simplifying this, multiplying top and bottom by 1 plus t all squared, we have 1 plus t all squared over 2 root 1 plus t. Now, since this is 1 plus t to the power of a half in the denominator, we can take this up, and so we would be subtracting 1/2 from 2. So we can write this as 1/2, 1 plus t to the power of 2 minus a half, which is 3 over 2. Okay, and so this is dy on dx. Now, if you don't believe that, then we can take an alternative approach by finding the relationship between y and x. Let's say alternatively, we can see that y squared minus 1 is t just from this right here. And so subbing that into x equals t over 1 plus t, we have x is equal to y squared minus 1 over 1 plus y squared minus 1. And so this is y squared minus 1 over y squared, or 1 minus 1 over y squared. Okay, and so we can differentiate this implicitly. So taking d on dx to both sides, on the left we have 1, and on the right hand side, the derivative with respect to x of 1 is 0. So we have 0 minus d on dx of y to the minus 2. Now this requires the chain rule here. So 1 is equal to minus dy to the minus 2 on dy times dy on dx. Okay, so differentiating y to the minus 2 with respect to y, we pull down the minus 2, and so minus 2 is plus 2, y to the power of minus 2 minus 1 is minus 3, dy on dx. Okay, now multiplying both sides by y cubed and dividing by 2, we have dy on dx is equal to 1/2 of y cubed. But if we go back here, so we can reconcile it with this and see what is y. Well, we have y equals the square root of 1 plus t. So we have 1/2 of the square root of 1 plus t to the power of 3. And so this can be written 1/2 1 plus t to the power of 1/2 times 3, or 3 over 2. So again, dy on dx is 1/2 1 plus t to the power of 3 over 2, matching what we have here. So we've done the same thing in 2 ways. Question 10. Find the equation of the tangent line at t equals minus 1 for x equals t cubed plus 1, y is t to the power of 4 plus t. So the ingredients here, we need to find the point in Cartesian coordinates where t is minus 1. We need dy on dx, and then we need to construct the equation y equals mx plus c. Okay, so first let's begin with finding the Cartesian point of interest where we're taking that tangent point. So x of minus 1 is minus 1 to the power of 3 plus 1, which is minus 1 plus 1, and that's 0. Y of minus 1 is minus 1 to the power of 4 plus minus 1, which is 1 minus 1, and that's 0. So the point of interest here is the point 0, 0. So tangent at 0, 0, and this occurs when t is minus 1. Okay, so next, x dash of t is 3t squared, y dash of t is 4t cubed plus 1. And so then, provided that x dash is non-zero, so when t is not equal to 0, x dash of t is not equal to 0, and so dy on dx is y dash of t over x dash of t. So this is happening when t is non-zero. So simplifying this, we have 4t cubed plus 1 over 3t squared, and this is dy on dx. So the slope of the tangent at the point where t is minus 1 is, let's call this m, 4 minus 1 cubed plus 1 over 3 times minus 1 squared, and so we get 1 minus 4 over 3, so that's a slope of minus 1. Okay, so now that we know that the slope is -1, let's write our equation of the tangent line, y equals mx plus c, so minus x plus c. Now we need to know what the c value is, but we get this from having that tangent point, the point where the line meets the curve, and that's the point 0, 0, right up here. Okay, so since 0, 0 is on both tangent line and the curve, 0 is equal to -0 plus c, and so we see that c is 0, and hence we get the tangent line y equals minus x, and we're done. Okay, I can see question 11 is identical to question 10. Don't know why that's there, so let's jump to question 12. Find the equation of the tangent line at the point 1, 3, 4. X is 1 plus the natural log of t, and y is t squared plus 2. So we get this point when t is 1. So when t equals 1, we get the point xy is, now e to the 0 is 1, so natural log of 1 is 0, so we have 1 comma 1 plus 2 is 3. So that occurs when t is 1. All right, and so then let's take x dash of t. So we have 0 plus the derivative with respect to t of the natural log of t, that's 1 on t, and then y dash of t is the derivative of t squared plus 2 with respect to t, which is 2t. Okay, and so 1 over t is non-zero when t is 1. We have dy on dx is y dash of t over x dash of t, which is 2t over 1 over t, and we can express this as 2t squared for all t, for all real t. Okay, so when t is equal to 1, we have dy on dx is 2 times 1 squared, which is 2. And so this is the slope of our tangent line. So we have tangent line y equal to 2x plus c. And so to find that c, we sub in the 0.13 and get 3 is equal to 2 times 1 plus c. And so c then is 3 minus 2, which is 1, which gives us tangent line y equals 2x plus 1. And there we have it. Okay, question 13. Find dy on dx and d2y on dx squared. For which values of t is the curve concave up? So we have x equals t squared plus 1, y equals t squared plus t. So x dash of t is 2t, y dash of t is 2t plus 1. So when t is non-zero, we have x dash of t is non-zero. So when t is non-zero, dy on dx is y dash of t over x dash of t, which is 2t plus 1 over 2t. And we can even write this, dy on dx is 1 plus 1 over 2t when t is non-zero. Okay, so differentiating again, so we can write this as d on dx of dy on dx. So just like this, and we can express this as d on dt of 1 plus 1/2 t to the minus 1 over x dash of t. And so differentiating that numerator with respect to t gives minus 1 over 2 t squared, and then x dash of t is 2t, provided t is non-zero, and so we have minus 1 over 4t cubed for d2y on dx squared. Okay, so alternatively, you can find the relationship between x and y and then implicitly differentiate that just to make sure you're on the right track here. All right, and so back to the question, for which values of t is the curve concave up? So d2y on dx squared is positive when minus 1 on 4t cubed is positive, and this occurs when t is negative. Question 14. Set up an integral that represents the arc length of the curve, then give a numerical estimate. So here we have x is t plus e to the minus t, y is t minus e to the minus t, and t is between 0 and 2. So the formula for arc length is it's an integral from beginning parameter to end parameter, so from 0 to 2, of the norm of r dash of t dt, where r is a vector. R of t is x component, y component, so t plus e to the minus t, then t minus e to the minus t. So we need to differentiate this. So r dash of t is the vector 1 plus minus e to the minus t, and then 1 minus minus is plus e to the minus t. Now calculating the norm of this vector, we have the square root of 1 minus e to the minus t squared plus 1 plus e to the minus t squared. Okay, and so that goes in here. So we have the integral from 0 to 2 of 1 minus e to the minus t squared plus 1 plus e to the minus t squared. Okay, so that's probably a difficult integral to do, but expanding this will make it look a little bit better. So let's expand this. So 1 squared is 1, 1 plus 1 is 2. Okay, so squaring this, the middle term is minus 2 e to the minus t, and then we have plus e to the minus 2t. Then the middle term of this is plus e to the minus t, and then we have plus e to the minus 2t. So simplifying that, these two vanish. We have 2 of these. Okay, so this is to the power of a half, and up here as well. So now let's open up Mathematica and calculate this numerically. So write n integrate exp minus 2t. We're integrating with respect to t as t goes from 0 to 2, and we get approximately 3.14156. That looks a lot like pi, doesn't it? Is that pi? Let me just check this. Very close anyhow. Question 15. Find the exact length of the curve. So this is an arc length problem. We have x equals 1 plus 3t squared. Y is 4 plus 2t cubed. T between 0 and 1. So remember, L is the integral from 0 to 1 of the norm of r dash of t dt. Now r here is the vector 1 plus 3t squared, 4 plus 2t cubed. So differentiating this, our dash of t is 6t, and then we have 6t squared. So taking the norm of this vector, we have the square root of 6 squared times t squared, so 36t squared plus 36t to the power of 4. So there's a 36t squared in both of these, so we can write this 6t root 1 plus t squared. Okay, coming back to our integral, we have the integral from 0 to 1 of 6t square root of 1 plus t squared dt. Now that integral looks a little bit hard, but I don't think it is really as hard as it looks, so let's let u be the inside function. It looks like it comes out with substitution here. So this is L. Okay, now we'll say let u be equal to 1 plus t squared. Let's take du on dt, and so we get 2t for this. So this tells us how to replace dt here. So dt can get replaced by du over 2t in a substitution. So let's go ahead and do that then. L is equal to the integral of 6t. Now we have inside here, that's u to the power of a half is our square root of 1 plus t squared. So u to the power of a half. Then we're replacing dt with du over 2t by substitution. Okay, but as soon as we replace the dt with a u or a du there, we need to replace these bounds of integration in terms of u. So note u of 0 is 1 plus 0 squared, which is 1. So the 0 was down here, so we have a 1 there. And then u of 1 is 1 plus 1 squared, which is 2. So we have a 2 up here. Okay, so we can see that we can cancel the t's. Let's pull out the 6 over 2, which is 3. And so we just have 3 times the integral of u to the power of a half du from 1 to 2. Okay, so now this is a power, so we can add 1 to the exponent since the power is not minus 1. 3 times we have u to the power of 3 over 2, adding 1 to the exponent. Now dividing by 3 over 2, that new exponent is the same as to multiply by 2/3. This is from 1 to 2. Okay, so now we sub in the 2. So let's pull out the 2/3 as well. And so we have the square root of 2 to the power of 3, and then we're subtracting 1 to the power of 3 over 2, which is 1. So this here we can write as 2 root 2. Let's cancel the 3's, so we have 2 outside of 2 root 2 minus 1. And so this we can express as 4 root 2 minus 2 is that arc length, or the exact length of the curve from t equals 0 to t equals 1. Okay, question 16. Evaluate this line integral over c of y squared dx plus x dy, where in part A, let's begin there, c is the line segment from the point P, let's call this minus 5 minus 3, to the point Q, which is the point 0, 2. Okay, so first thing we want to do is parameterize this line segment. So the line, or the vector PQ, is the vector Q minus P, which is 0, 2 minus 5 minus 3. And so for this, we get 5, 5 as our vector. Okay, and so to parameterize this line, we've got r of t is that vector PQ times the parameter t plus one of the points. Okay, and so if I just choose the easy one, q, then we've got plus 0, 2. Now what this is, okay, so let's give a sketch of this as well. We've got the point minus 5, 3 here, and then here is our point q. So from P to Q. So r is the origin to a point on that line segment. Okay, and so when t is minus 1, we've got r of minus 1 gives the vector minus 5 minus 3, and so that's O to P, and so from this we can obtain the coordinates of P, which is the point minus 5, 3. All right, so when t is equal to 0, r of 0 is the vector, just subbing in 0 there, we've got the vector 0, 2, which is from O to Q. And so from that, we can obtain the coordinates of the point Q. Okay, so our parameterization here of that line segment is r of t is 5t, and then 5t plus 2 for t between minus 1 and 0. All right, so in the next part of this, we want to look at the y squared and the x and form a vector f from that. So let's say let f be equal to y squared x. Okay, and then now the integral over c of y squared dx plus x dy can be expressed as a dot product of the vector f with the vector dx dy. And so this is the integral over c of f dot dr. Okay, so now we can, since we have a parameterization of r, we can replace this in terms of this. So from minus 1 to 0, f of r of t dot dr on dt dt, which is r dash of t dt. Okay, so continuing on, this is the integral from minus 1 to 0. Now f of r of t, what we do is we take f and put in our parameterization in for the x component and the y component. So that is 5t plus 2 squared, and then 5t, and then we dot this with r dash. So r dash here, just differentiating r with respect to t, we have 5, 5. Okay, now taking this dot product, we have 5 times 5t plus 2 squared, and then plus 25t dt. So now to integrate this, let's expand that. So 5 squared is 25. 5 times 25 is 125. So we have 125t squared. 5 times 2 is 10 times another 2 is 20. 20 times 5 is 100. So 100t plus 25t is 125t. And now we have 4 times 5 is 20 dt. Okay, let's integrate this. So 125 over 3t cubed plus 125 over 2t squared plus 20t minus 1 to 0. Okay, when we sub in 0, we get 0. So we've just got 0 and then minus in brackets 125 over 3 times minus 1 cubed, which is minus 1, plus 125 over 2 minus 1 squared is 1. And then 20 times minus 1 is minus 20. Okay, so simplifying this, we have minus in brackets, minus 125 over 3 plus 125 over 2 minus 20. Now we want to put this all over 6. So we have 125 times 2 over 6. I put the minus in as well. And then I'm multiplying top and bottom of this by 3. So minus 3 times 125 over 6. And then 6 times 120, but the minus comes in, so it's a plus. 120 times 6, 20 times 6 is 120. Okay, so simplifying this, now that it's all over 6, we've got 250 minus 375 plus 120 all over 6, which is 370 minus 375, so minus 5 over 6. And we're done. 16 part B. So we're evaluating the integral of f dot dr over the curve C, where C this time is the arc of the parabola x equals 4 minus y squared from the same point minus 5 minus 3 to the same point 0, 2. Okay, so let's write down our key data here. We've got the force field y squared x, and then we can parametrize this path as a function of t using x equals 4 minus t squared, y equals t, and then as t goes from minus 3 to 2. And if you check this, when you put in minus 3 here, you have 4 minus 9, which is minus 5, and minus 3 down here. So you've got the point minus 5, 3 treated as a point. Remember, this vector r is the vector from the origin to the point. And so we get a description of the point. Now, when we sub in t is 2, we have 4 minus 4 is 0, and t is 2, so 0, 2. So the vector r is the vector from the origin to the point 0, 2. But from that, we can understand the point 0, 2. Okay, so now our integral, our line integral, f dot dr, we can write this as minus 3, 2 f of r of t dot r dash of t dt. Okay, so substituting these values in, f of r of t, we take this t, put it where we see the y, so that's t squared, and then we take our x value of r, we put it where we see the x, that's 4 minus t squared, and then we differentiate r of t, and so we have minus 2t, 1, okay, and so now we need to take this dot product, so we have minus 2t cubed plus 4 minus t squared, and we integrate this, we have minus 2 over 4 t to the power of 4, so minus a half t to the power of 4 plus 4 t minus a third t cubed minus 3 to 2. All right, so subbing in the 2, we have 2 to the power of 4 divided by 2 is 2 to the power of 3, so this is minus 8. Then we have 4 times 2 is 8, so plus 8. Then we have 8 over 3, minus 8 over 3. Now subbing in minus 3 here, we have minus 3 to the power of 4 is 81. In brackets, minus 81 over 2. 4 times minus 3 is minus 12. And then minus 3 to the power of 3 is minus 27. Minus 27 over minus 3 is plus 9. Okay, so simplifying this, 8 minus 8 is 0. So we have then minus 8 over 3 plus 81 over 2 minus 3 is plus 3. Okay, so we want to express this over 6. So multiplying 8 by 2 gives 16, so minus 16. Multiplying 81 by 3 gives 243. And then 3 times 6 is 18. Now that it's all over 6, we can add our numerator and simplify this. And so we have 18 minus 16 is 2. 2 plus 243 is 245. So 245 over 6. Question 17. Find the work done by the force field F equal to the vector x squared minus xy in moving a particle along the quarter circle. So we have a parametrization of that quarter circle. And again, so this is going to look like this, but we have the arrow or vector r from the origin to a point P on that quarter circle. So this is given by
cos of t sine of t for t between 0 and pi on 2 radians. Okay, so the work done is the integral over c of f dot dr, which we can write as the integral from 0 to pi on 2, since we have that parametrization, f of r of t dot r dash of t dt. Okay, so f of r of t, we just take these components of r and we sub them in there. So that's cos squared of t minus cos of t sine of t, and then the derivative of the vector r with respect to t is minus sine t cos of t. So we then take this dot product and integrate the result. So cos squared times minus sine is minus cos squared sine of t, and then again we have minus cos squared sine of t, so we have two of those, minus 2 cos squared t sine of t dt. Okay, now to integrate this, we can do this via substitution by letting u be equal to cos of t. Okay, and so that's minus 2u squared sine of t. We need to replace this dt in terms of du, so to do that we differentiate taking du on dt. We get minus sine of t, so that tells us that we can replace dt with du on minus sine of t in here. Okay, but we also need to, as soon as we replace the dt with du, we need to replace the bounds of integration also. So u of 0 is cos of 0, which is 1. U of pi on 2 is cos of pi on 2, which is 0. So then we have the integral from 1 to 0. Now, usually you have the greater number at the top, but we can swap these around with a minus sign. I'll show you in a moment. Okay, so we're integrating minus 2u squared sine t dt, but we can replace dt with du on minus sine of t, and so the sine of t vanishes. So we have 1 to 0. Cancel the minus with the sine, minus sine of t. So we have the integral of u squared du. Now, next we will swap these around so the bigger number is at the top. But when we do that, we introduce a minus sign. Okay, so now let's integrate and sub in those numbers. So we have integral 1/3 u to the power of 3. So minus 1/3 u to the power of 3, 0, 1. Where did the 2 go? There was supposed to be a 2 in here. So let's put the 2 back in here. This 2 here. This is minus 2/3. U to the power of 3, 1 is 0. Okay, and so this is minus 2/3 minus 0. So minus 2/3. Question 18. Consider the vector field f 3 plus 2xy, and then y component x squared minus 3y squared. Evaluate the line integral over c of f dot dr, where r of t is the vector e to the t sine of t, e to the t cos of t, for t between 0 and pi. Okay, and so we have integral over c of f dot dr can be expressed as the integral from 0 to pi f of r of t dot r dash of t dt. Okay, subbing in, replacing the x with e to the t sine t and the y with e to the t cos t in here, we have 3 plus 2 e to the t sine t times e to the t cos t. There are two of the e to the t's multiplying, and so that's e to the 2t sine t cos t. And then e to the t squared is e to the 2t sine squared t minus 3 e to the 2t cos squared t. And then we need to differentiate e to the t sine t. So using the product rule, so I'll put this down here, we have e to the t cos t plus e to the t sine t. And then for this, we have e to the t times the derivative of cos is minus sine plus e to the t cos of t. Okay, now carefully taking that dot product. So you can see here that you get a little bit of a mess, right? Which can be simplified. However, is there an easier way? So the answer to this question is yes, there is an easier way. We don't have to follow through with this mess. Okay, so what we want to do instead here is let's let g be equal to the vector 3 plus 2xy, x squared minus 3 y squared 0, and then let's take the curl of this vector. So the curl of G is, and you can verify this, that it's the 0 vector. I won't show the details here, but it's the 0 vector. And so that means that f is a gradient field, hence there's a potential function. So it's the gradient of the scalar function f. Okay, and so now to find this, we put f subscript x equal to the x component, 3 plus 2xy, f subscript y equal to x squared minus 3y squared. And so integrating the first equation gives f equal to 3x plus x squared y plus some function, let's say lowercase g of the other letter of y, so that if we differentiate this line partially with respect to x, this is what we get. Okay, now differentiating this partially with respect to y, we can compare that with this. So f subscript y gives 0 for this part, and x squared for this, and then plus g dash of y. Now we can compare that with this line. So this is supposed to be equal to x squared minus 3y squared. So now we can see that g dash of y is minus 3y squared. Okay, and so integrating this with respect to y gives g of y equal to minus y cubed plus some constant. And so then that tells us that f of x and y is 3x plus x squared y minus y cubed plus a constant. But here we don't need the constant, we just need one potential function that's going to work out for this. Okay, so given that we found this potential function, we can use the fundamental theorem for line integrals. So by the fundamental theorem for line integrals, the integral over c of f dot dr is the integral over c of grad f dot dr, which is f of our last point in the parametrization. So e to the pi sine of pi is 0, and then e to the pi cos of pi is minus 1, so minus e to the pi, and we subtract f of the first point in our parametrization. So e to the 0 sine of 0, this is 0. E to the 0 cos of 0 is 1. Okay, so with f being this function, we have 0, 0 minus e to the pi cubed, and then we're subtracting. So let's put brackets in here. So again, we have 0, 0 minus 1 cubed. Okay, and so simplifying this, when we cube this, we have minus e to the 3 pi, but there are two minuses here, so this is plus e to the 3 pi. And then over here we have two minuses, so we have a plus 1. So e to the 3 pi plus 1.